up pretty nicely on your, when I made these notes, they lined up nicely. When I somehow took a picture of it to put it onto the smartboard, the little yellow rectangles don't match up as nicely as they do in your notes. But here's the idea of what we're going to be doing next. We are going to be using them, finding out the main application of integrals is that you can now find areas under curves. And that idea of areas under curves is connected to the definite integral. So up till now, we've been doing the indefinite integral. The indefinite integral is working backwards from a derivative, adding the plus c. The definite integral involves numbers. It gets a value, and the value that you get is an area under a curve. So here we have, looks like almost like a sine or a cosine graph. And if you wanted to find the area represented by the shaded region S, it would be hard because you have a curve. Here's the idea of calculus, is that, and here my rectangles are not very lined up, but if they were lined up like they are in your notes, figuring out each of those rectangles would not be hard, because an area of a rectangle is length times width. And the area of the yellow part would be a fairly good estimation of the area of the gray part. And if the rectangles were even smaller, it would be an even better estimation. And if we made the rectangles infinitesimally, really small, infinitely small, then you would basically have a limit that would be that area completely. So that is the idea that we're going to be looking at. Now, I'm going to go into some of the theoretical idea right now, and you're not going to have to reproduce this. You get to, in this class, you get to just enjoy the fact that we went through it, we accept that it happens, and then we just apply our new knowledge to it, okay? But here's what's going on when we're looking at it. If we take one little tiny rectangle and look at it separately, okay? We could have a smaller rectangle which matches up to the start of the function, a bigger part of the rectangle at the top which goes up to the next y value of that function. So what we could say here is that the area of this smaller rectangle is less than the right amount, and the area of the bigger rectangle is more than the right amount. Okay? So the area of the shaded part is somewhere in between there. It's a delta symbol. Well, it's, yeah. Yeah. And it's because we use dx's all the time for calculus. Question. Okay. So what we have is this y dx. If I underline that in green, that's this rectangle. And y plus dy dx, that would be the big rectangle, is the actual shaded area is somewhere in between. Okay? Now, if you multiplied or divided everything by dx, in this case, which is this little small part, and this is where a little bit of hand waving comes into play, because then we get a dA dx in the middle, and we get y plus dy. We can now integrate this idea. So this part in between represents the average rate of change, which is a derivative, and if you make dx go to 0, if you make it infinitesimally small, then it's the actual derivative. So this is the idea, which means that we turn our equation, and this is where the symbol's italicized delta there. As it goes to 0, it becomes the actual derivative. And this would also mean that dy would go to 0 as you make it really small. And then the inequality becomes this. Because what did we have before? Before, let's just go back. Before we had a plus dy here, because that's a little bit at the top, and we had dA divided by dx, those are actual values, really small. But if you make them go to 0, then this one would go to 0. So the right-hand side would just become y. And the middle section, as you go to 0, would just become the derivative. So now what you have is an inequality where y is less than something and then less than y. So this means that y has to be equal to dA dx. And if they're equal, if we now integrate both sides, since we have the derivative here, integrating the derivative would just get what you had originally. And we have that the area is just the integral of y dx. Okay. Really cool. So this equation will give us the area up to any value of x that we choose if we want to find the area between two values of x, right? Like we had in that area from b, and then you subtract the area up to a, you'll get the area in between a and b. And this introduces what's called the definite integral. So the indefinite integral, here's a new definition for you. My highlighter is working wonderfully today. The definite integral, it looks like the indefinite integral, except you add numbers to the bottom and the top of the integral. And that means you're finding the area under the curve from the value a to the value b. And it's called the definite integral because you actually get a number. Indefinite integral gives you an equation with a plus c. Definite integral will give you a value because it's calculating an actual area. So a is the lower limit, b is the upper limit. And to find the definite integral, we do the same thing like we do with the indefinite integral. But now we put that answer, we don't worry about the plus c. And we put our a and b values in there, and then all we have to do is plug in b into the new function, plug in a into the new function, and subtract them. It is really quite straightforward and quite simple. So we'll see what that looks like with a couple of examples. Hey. So for those of you with a graphing calculator, there is a way to do integrals on there, areas under curve. Maybe we'll look at it after we do an example to see it on our calculator as well. Yeah, just do the calculator. Perfect. Yes? Back a couple slides. Okay.
How come y is less than y? That's a good question.
So this part here, if you got something like this, right, because y technically cannot be less than y can only be equal to y. But we started off with a situation which definitely could be this green rectangle is definitely smaller than the blue rectangle, which is definitely the shaded part is in between. That's where we started. But as things got smaller, in other words, as the dx went to 0, everything shrunk together that eventually it was equal. If you made it super small, as infinitely small, a limit as small as it could get, then it would basically be equal. And that's what happens in the next slide. They're saying, if we did that limit, then the right side would be y, the left side would be y. This actually doesn't make sense, but what does it imply? It implies that they have to be equal. In other words, I picked a number. The number that I picked is between 3 and 3. Can you guess what number I picked?
4.
The only possibility is that it is 3.
So why no
Equal sign?
or equal?
Right. So why not have this all the way through? Because when we started, it definitely wasn't equal. So it wouldn't be true where we started off.
It could be equal if you had a flat line.
Oh, fair enough. So maybe in that situation, if it was a flat line, there could be a possibility of an equal part there. But the diagram that I showed didn't have that equal sign. Yeah, it would be interesting to look up official proofs. Do they have an equal sign in that section? Or is it just mathematically accepted that when you have this situation, this can't be true. The only thing that this says is that it must be equal. So here's our first example. As far as notation goes, we would first do the integral. Oh, there's an x missing here. We would first do the integral of the inside, the indefinite integral, without having to write the plus c. But we put it in a square box, and we write the upper and lower bounds as they appeared. So in this case, 2 and 5. Then, plug in 5, plug in 2, and subtract. So plugging in 5, I get 3 natural log of 5. Plugging in 2, I would get 3 natural log of 2. Typing that into my calculator, I get 2.75. What did we just find? Okay. This is the graph. Oh, sorry. I drew the wrong graph. This is the graph of 3 over x. When you plug in 2, you would get 2 comma 1.5. When you plug in 5 for x, you would get 5 comma 3/5. And this little section here, we just calculated the area from 2 to 5 under the curve 3 over x to be 2.75-ish once we rounded it, which is pretty cool because this curve part makes our life difficult in all of our math up till now. So if we do this with the calculator instructions here, some of the things you can do on our calculator. So for those of you that have a calculator, which one do I have first? The second trace. Oh, first of all, we can write our equation, 3 divided by x into y equals. There's our 3 over x graph, okay? Second, calculate. Number 7, the integral, lower limit, type in 2. Upper limit, type in 5. And it shades it under there for us and says that the area, or the integral, is 2.7488722. Really quite nice. Okay? Other thing on our calculator that we can type in is hit the math button. Oh, I should go out of here, clear this. Hit the math button, go down to number 9, where it has integral. Depending on what version you have, you can type it in exactly as you see it. So we're going from 2 to 5. No, some of them are not very nice. 3 over x in terms of x. Push enter, and it finds the answer that way as well. Nice thing about this is if you've done it by hand, if you've showed all your work and done the calculus and get an answer, here's a way for you to check the answer instead of having to look in the textbook at the back of the book. So just like indefinite integrals, we have to use our skills to integrate. How do we integrate x plus 1 over x squared? Is it integration by parts? Is it substitution? Is it something that we know how to do directly? We just don't know it whatsoever, and we skip this question. It was too hard. Go on to the next one. What would be a strategy we could use in this situation? Okay? So if I'm a student, I'm coming to this question, I would probably think, first of all, ooh, I like to do substitution because I see a function inside of another function. The x plus 1 over x is inside of the squared. But unfortunately, I don't see its derivative anywhere near that, because the derivative of the x would just be a 1, and the derivative of 1 over x will be an x to the negative 2, and I don't see any x to the negative 2s. So that doesn't work. So then I think about integration by parts, but I only see one thing, not two things. This would be a situation then I say, well, can I do anything with the equation? And yes, I can square it. So I can multiply it by itself and see what I get. And if I do x plus 1 over x times x plus 1 over x, I'm going to get x squared plus 2 plus 1 over x squared. You can do that off to the side. Right? You would just have to FOIL or multiply or distribute, whatever language you like. Multiply that all out. X times x will give you x squared. 1 over x times x will give you 1, and that'll come twice. That's why we have a 2. And 1 over x times 1 over x would give you 1 over x squared. If you'd like to go for a walk and get a drink of water, that's okay. Now, with a definite integral, what you can do is you take your integral of the inside, put square brackets around it. So the integral of x squared, add 1 to your exponent and divide. Integral of 2x would just be, of 2 would just be 2x. And the integral of 1 over x squared, think of it as x to the minus 2, add 1 and divide. Probably I would have had that written off to the side like that. So you can see why the sign becomes a negative and we get a 1 over x. Now we plug in 4, get a value, put that in one set of brackets, plug in 2, put that in another set of brackets. And the rest is just calculations. Right? Some things you might be able to simplify within. And as a result, you get 275 over 12. Of course, you could do all those calculations. They would just take time, which rounds to 22.9. And I just have units squared there. You wouldn't need the units squared. But we're talking about area, so it is a question. Sometimes these questions will have units involved. And if you graphed it on your graphing calculator, because probably you didn't know what x plus 1 over x graph looks like. There's an asymptote in the middle. Almost looks like the letter W. Ooh, or it looks like a dolphin diving, eating the y-axis. Yeah, not bad. So we found the area between 2 and 4, and our calculator is reiterating that the math that we did was correct. Question, you look like you're in your mental math calculations. Here, I can scroll up a little bit so you can see more of them if you'd like. Why don't you try the next one on your own? Yeah, I can plug it in. Yeah, I can plug it in here and then you can charge it. So that'll be 4 cubed is 64. Did you write 48? Let me just charge. You find it? Perfect. Yeah, pick it up tomorrow. Yeah. It's So I'll put up the answer for this one so you can check how you're doing. There is the integral of e to the 3x and the integral of 2 over x plus 1. So again, everything, the derivative rules that we learned early on, they come back in our integration. And the integration we learned early on, it comes back again in definite integrals, so we have to be really good. Here, the e to the 3x would stay the same, but you would have a chain rule, so we have to divide by 3. And then we have our natural log. So then you plug in. I like to make one big set of brackets where I plug in the 1. Then I put a minus sign, a big set of brackets where I plug in the 0. And now it's just a matter of here doing our calculations. Oh, that one I didn't make go away. Oh, there it went. It was just lagging. And I get approximately 4.98. So basically, after finding the integral, everything else is plugging in a number and finding values, stuff that you've done a fair bit in the past. Not very hard, especially if you have a calculator. You could probably type in all of that at once. Now, once you go to universities, I was just actually a couple weeks ago, a former student was getting ready for his Calculus 2 exam and wanted some help, so I helped him study for a little bit. And all he had to do for his university classes is he would have to show the formula he would use and plug in the value, and then he could leave your answer like this. Sometimes they wouldn't even have to, like, this still has a step to do with plugging in to know that you have to plug in the 1 and plug in the 0. And he might have had to simplify it to look like this. But no other calculations were necessary. Just leaving answers as very complicated looking things without finding the answer. Which was a little bit hard and frustrating because if he was doing his exercises in the textbook, his exercises in the textbook had an answer. So he's like, I don't know if I'm doing it right because I know that I don't have to simplify any more than this. But actually doing the plugging in and solving would take me another 10 minutes, and I don't really want to do that. So I actually, for him, I introduced him to Wolfram Alpha. I don't know if you guys are aware of that, of that website, but check this out. I'll show it to you. It is the Google of all things mathematical. Okay, so this is what we're finding. We're finding the integral of 0 to 1 of e, and you can be bad notation stuff, e to the 3x minus 2 over x plus 1 dx. All right, let's just do that. Let's see if it knows what I'm talking about. So I just said I want the integral from 0 to 1 of that. Do I need to close another bracket? Looks like I do. There we go. And it's so nice, it even highlights the brackets when I close them. Push enter. It translates it into nice notation that we had, so you can check, yes, that is what I want to find. Oh, I needed brackets here, so you're right. Let's close that up and try it again. There it is. It calculates it for you, gives you the right value. It draws the graph to show you the area under the curve. It does some mathematics beyond what we need to do. It shows the indefinite integral with the plus constant if you wanted to. And sometimes you can see more work. If you want a step-by-step solution for this, you can pay them money, and they'll show you. They got to make money somehow, right? Their own ad they're showing us. But it is very cool, right? You can type in anything in here, like Canada versus the US. Oh, look at this. What kind of math can we do? We can do the total area of the two countries. We can find the land area. We can find population and compare it. Population density. Right? Every square kilometer we have 4 people. Every square kilometer they have 36 people. Right? Ooh. Population growth. We're making more Canadians than Americans are making Americans. Oh, this is what I've been looking, right? Once I get 83.6 years old, I'm going to move to another country that has a longer life expectancy, and that will guarantee mathematically that I will live longer, right? That's how it works, right? That's right. What's the best life expectancy? Well, if we click on life expectancy within here, does it just show, I guess you could just take life expectancy and there we go. Highest is Monaco. That's where I'm going to move. Apparently, it's really cheap to live there. And don't move to Afghanistan. You're only going to live to 53. Those are guaranteed, right? Yeah, and in fact, in Monaco, they euthanize anyone over 89.4. No, I'm kidding. I shouldn't have put that in the video. That sounds terrible. Okay. Back to our examples. Try to do the setup for this one. I will give you the numbers. In fact, for each of the D, E, and F, try to do the setup, and then I'll give you the numbers after that. But you now know that if you want to, you can use a website like Wolfram Alpha to get you the numbers right away. And it will tell you anything mathematical. Right? You could probably ask, what is the 2 millionth digit of pi? And it will tell you that. Oh, take away all your fun? You've got to have something to do tonight. All right, how was your setup? Did you remember the negative with cos? Oh. This one would be a non-calculator one. Because what happens when you plug things in? You get your unit circle values. You need to know those for this course. Why did you do that? This is not so bad. Think about your circle. Where's 3 pi over 2? Down there. Cos is your x coordinate. That's going to be 0. What's cos of pi over 2? 3 times pi over 2, plug in that one first, minus this one. Top one minus the bottom one. Whew! And then the mental math at the end is just excruciating. Now, when we draw the picture, something interesting happens. When we draw the picture and we look at it, and it shades it in, how is that area 0? And when you integrate and find areas under curves, it considers areas above the x-axis as positive and areas below the x-axis as negative. So in this situation, the one area canceled out the other area. All right. How did your integration setup go? This is an ax plus b integral. Oh, sorry. Then I'll go like this and go, oh, try this one. There we go. How was your setup? Add 1 to the exponent, have to divide by the 5, and then because of ax plus b, there would have been a chain rule which multiplied by 2, so we divide by 2. And it is possible to have, notice in this question what's weird? The number on the bottom is bigger than the number on the top. Okay? That does not technically, what it's figuring out, it's the area from 2 to 0, and then subtracting the area from 3 to 0. So you're allowed to do that. And when you get your result, it might make sense to you that the area is negative. Whoa. So the integral of x will be add 1 to the exponent, divide, so x squared over 2. And the integral of e to the negative x would be e to the negative x divided by a negative 1, which will make the sign out in front back to positive. I mean, if you wanted to, you might have showed your work like this, right? That would be fine as well. Because e to the negative x would stay e to the negative x, but then you'd have to divide by negative 1 because of that chain rule. And then dividing by that negative 1 would have made that like a plus sign. Then it's just a matter of plugging things in. And that's what you would get with your calculator. Crazy. So on the next page, we have a list of properties of our definite integrals. And many of these are similar to properties that we've seen with indefinite integrals, but some of them are specific to definite integrals. For example, the first one. If you wanted to find the area under a curve and you started at some value, let's say 5, and you went to 5, there'd be no area under that curve because it would be just a straight line, which has no area. So does it make sense that that would equal 0? Secondly, we saw this already when we did something in the wrong direction. If the integral from a to b is one number, if you did the integral from b to a, that would be a different number. Now, technically, the easiest way to see this is, let's say I take a parabola, right? Here's our parabola, and let's go from 1, 1 to 3, 9. Technically, what we're doing is when you figure out the integral from 1 to 3, you're taking the area from 3 all the way down to 0, and then subtracting the area from 1 all the way down to 0. And you would get one area, which I could shade all of this in green, and then you would subtract the area that I had in red. So let's say the green area is 5 and the red area is 1, you'd have 5 minus 1. If you did it in the opposite direction, then you would get 1 minus 5. And it should make sense that whenever you subtract in the opposite order, it's just the negative of the other one. So if the area from A to B was 4, then the area from B to A would be negative 4. And sometimes we're going to be like, if I'm finding the area from A to B, I can take a new value in between, and that's going to equal the area from A to C, a little section of it, and then take the area from C to B, add them together, and that would be the whole area. Now you might say, well, why would that be important? Because we will get some questions, like the sign question here. When we look at the graph, sometimes you'll get questions that say, find the integral, and sometimes they'll have questions that say, what is the actual area bounded by the curve and the x-axis? And in this situation, you'd have to add those two parts together. And you would need to find the point C that was in between. So you could figure out from A to C and make that positive. Then figure out from C to B. You'll get a negative number, but since you want the actual area, you'll take the absolute value of that and make it positive. And so that is the purpose and the reason why item number 3 is important. And just like indefinite integrals, if you have a constant inside, you can move that constant outside. The nice thing about that is it might make your calculations easier when you're doing plugging in B and plugging in A. You're dealing with smaller numbers rather than dealing with bigger numbers. And just like the indefinite integral, if you're adding and subtracting, you could do the integral all by itself, or you could do the integral of each part separately. Every time. As much writing as possible is always nice. Okay, so there's some question here that get us to think about our properties. These are property-specific questions. Without knowing what the functions actually are, you can answer all of these questions. Let's see how you did on this one. So what I would do in this situation, I would say, hey, if I'm subtracting, that means I can do them separately. Then the 3 out inside, I could bring that 3 out in front. So this is just rearranging this using the properties. And then we were given that the integral from 0 to 2 of f of x, that part was 4. And we were given the integral from 0 to 2 of g of x, that part was negative 3. So now you could just plug things in and get our answer to be 15. This is a 2. It's a 2 on the top here, and a 2 on the top there, because it's a 2 on the top. It still has to be a 2. It doesn't change because that wouldn't be allowed. Yeah, it does kind of look a little bit like it. It's, yeah, fx, it's, yeah. This just means they're given that there's some function. Maybe it's x squared plus 3. You don't know what equation it is, but they tell you that the area under the curve of that function when you go from 0 to 2 is equal to 4. Even though you don't know what the function is. It's just 4. So if you can rearrange this to get 0 to 2, right? Yes, exactly. Good on this first one? Okay, try the next one. Here we go, checking the next one. There we go. Don't be afraid to ask questions. And all good on this one? Got negative 12? So here we have from 5 to 2. And we need to, the given was from 2 to 5, so we put a minus sign in front using that property. You like these little puzzle solving ones? Just this for the rest of the year. Okay. I can find some tough ones. No. They're not too bad, right? Ooh, 0 to 5. Because there's no 0 to 5, right?
Yeah, I was thinking like 12 minus 4.
Mm-hmm.
You just can't get it.
No, you can. You have to use this one. Yeah, if you draw pictures of what's happening. Mm-hmm. 0 to 5 is same as going 0 to 2 and then 2 to 5. Look at the rules. But here, look, so here's some curve. Woo! Okay? Here's 0, here's 2, here's 5. We know the area from 0 to 2 is 4. We know the area from 2 to 5 is 12. What is the area from 0 to 5? You just add that together, right? 4 plus 12 is 16. Okay. In a question like that, the given things would be there. You would not get a list of the properties you would have to know and memorize, or hopefully they just make sense to you, the properties, and then you apply them from here. So I'll show you the answer for this one. 0 to 4 would be the same as 0 to 2 and then 2 to 4. Right? Which ones do we know? We know 0 to 4 is 6. We know 0 to 2 is minus 3. So just rearranging this, we get the area is 9. And is this the last one? Or is there an F? Let me see if I remember. No, that is the last one. Here we go, the last one. This is the trickiest one.
That's the one where I invented math.
You invented math and it works. F of x plus 3 is f of x translated 3 to the left. So this is the same as thinking from 0 to 2 of the original function.